All right, here we go. Torque and rotational inertia. Do you want to say hi, Peter?
Hello.
Hello. That's Peter. He's hanging out. All right, so most of this stuff should be a review from what we learned last year, so I'm not going to spend a ton of time on this. There's one type of problem that we're going to do this year that is different from what we've done in the past. But before we get there, let me give you a super quick crash course in torque. At the beginning of the year, we learned Newton's laws, and one of the things we learned is this idea that net force causes acceleration, right? And last year in honors, hopefully you learned that in a similar way, net torque causes angular acceleration, right? And so torque is a measure of how much a force causes an object to rotate, all right? So the connection lies in these two equations. So net force, Newton's second law tells us that net force is mass times acceleration, right? So last year we learned that the angular counterpart for that was this, that net torque is equal to rotational inertia, the counterpart to mass, times angular acceleration. Okay? So how do you produce a torque? Well, what we learned last year was that the torque produced by a force is proportional to two values. Okay? It's proportional to the amount of force applying the torque, the force that's attempting to make your object rotate or change how it's rotating, and then the distance d between the pivot point and the point where the force is being applied. And remember, we called that the lever arm. All right? And so the equation to calculate torque is actually, it requires what's called a cross product. When we did work, we learned that work is force times displacement. And I used this little dot here. That little dot represents a dot product, okay? And it results in a scalar, right? Work does not have direction. All right? So this chapter, we're going to be doing torque. And again, we're multiplying kind of a displacement by a force, but this time we're using what's called a cross product. And so the notation is slightly different. We use an x to represent cross product. And different from a dot product, when you do a dot product, you get a scalar. When you do a cross product, you get another vector. So torque, much like force, is a vector. Okay? So a lot of times books give this equation, df sine theta. So d is the length of your lever arm, f is the magnitude of the force, and theta is the angle between those two vectors. All right? I don't tend to do it that way. The way that I prefer to do it is this. To remember that your torque is equal to your force times the length of your lever arm, and you need the component of the force that produces the torque is the component of the force that is perpendicular to your lever arm. Okay? Or equivalently, you could multiply the force by the component of the lever arm that's perpendicular to the force. Okay? Ultimately, I think that's going to be most easily explained by doing an example. So let me put my arrows on this. Do I want to do this? Yeah, I guess this really just gives you magnitude of the torque, and then you'll have to kind of think about the direction. All right? So have I said everything here? Yes, good. All right, so let's do some examples. All right? So here we've got a wrench. Okay? So our wrench presumably is trying to loosen a bolt or a nut or something. All right? So our pivot point is going to be, our pivot point is going to be right here. All right? I will usually try to mark my pivot point with a letter P. Okay? Now, remember, torque is the magnitude of the force which is perpendicular to your lever arm. Okay? So, suppose I exert a force over here of, I don't know, let's go, 8 newtons, right? Okay? So, for that particular force, we'll call that force 1. For that particular force, the lever arm is the length of the line from your pivot point to where that force is being applied. So this line here would be my lever arm, corresponding to that force. Okay? And notice, in this particular example, the force that I've drawn is perpendicular to my lever arm. So to calculate this torque, it's simple. You just do force times distance. So 8 newtons times, I'm going to grab the little ruler here and measure, oops, that's not what I wanted to do. Measure our lever arm. It looks like it's about 10 centimeters, so we'll call that 0.1 meters. And so our torque here is 0.8 newton meters. And then the direction we're just going to keep track of as being either clockwise or counterclockwise. So you can see with this pivot point, This is going to cause the wrench to rotate that way, which is clockwise. So this torque is actually negative. Okay? Now, what if we had a force? Well, I guess I don't know that I need to run through this example, but obviously if we moved the force over, that would produce less torque, right? Because then your lever arm would be itty bitty, right? Okay? So, what if instead, what if we had a force that was at a weird angle? All right, so let's do that. Let's have a force be applied, I don't know, maybe here. All right, we'll call this force 2, and we'll have it be like this. All right, so here's force number 2. All right, we'll stick with 8 newtons, I guess. All right, and then let's make our angle here be, I don't know, about 60 degrees. Okay? So, the idea is that force has components. One of those components is just pushing in towards the pivot point. That's not actually going to produce torque. All right, the component that's going to produce the torque is the vertical component, okay? Because that's the component that is perpendicular to my lever arm, right? So here's lever arm for force number 2. So torque 2 should be the force 2, but just the component of it that's perpendicular to the lever arm times the length of the lever arm. So what we'd need to do here is we'd have to draw out that vector, and we'd have to go, all right, well, here's my force, 8 newtons. We got 2 components. One of them's perpendicular, one of them's parallel. All we care about is the perpendicular one. This angle here is 60 degrees, so we're going to have 8 newtons times the sine of 60, which is, I don't know, 6 point something. Peter, what's 8 times the sine of 60?
Obviously 4.
You were close. 6.92.
I'm not number.
A valiant effort, my friend.
Thank you. I was only 2.92 off.
Uh-huh.
It's less than the guys at MIT, I guarantee.
All right, have a good day/weekend. Tell your sister I said hey.
All right.
That sounds really creepy. All right. Okay, so now we can find our torque. So our torque is the component of the force that's producing torque, 6.92 newtons, times the length of our lever arm, which I guess I need to measure, right? And I foolishly lost my ruler. So our lever, oops, dang it, I did it again. So our lever arm is, here we go. Oh, we'll call that 0.4 meters. Times 0.4 meters. So multiply that out and you get some number, right? All right, so you get 2.77 newton meters. All right, and again, that force is attempting to make the wrench rotate this way, which is clockwise, so it's going to be negative. Okay? All right, so 2 special cases that are worth pointing out. And really, the first one I probably should have done before I just did that green example there. Suppose I exert a force here, like this. All right, well then my lever arm would be this green line, right? And there, my force is parallel to my lever arm, right? So there is no component of force that's perpendicular to my lever arm. And as a result, no torque is produced, right? In English, pushing this way isn't going to make the wrench rotate at all, right? So that's no torque, okay? All right, and then finally, if you push right here in any direction, the length of your lever arm is 0, right? And so similarly there, your torque is going to be 0 because the length of your lever arm is 0. Okay? So that's the deal. We're interested in the component of the force that's perpendicular to the lever arm. And then you multiply that component by the length of the lever arm. Now, one thing worth noticing, when you calculate this, you can do what we just did, which is, in this example, in all of those examples, we found the component of the force that was perpendicular to the lever arm. Sometimes it makes more sense to go the other way, to find the component of the lever arm that's perpendicular to the force. All right, here's a simple example of that. Suppose our wrench looked like this, okay? And suppose that I pulled straight down on it here with a force which I will call force 4. All right? So option 1 would be to say, all right, well, here's my lever arm, right? And then we'd have to find the component of the force that's perpendicular to that. So you'd go, all right, well, here's my perpendicular component. Here's my parallel component. And then, you know, multiply this component by this, okay? And that totally works, all right? In fact, it's probably worth doing this, all right? So let's see, for simplicity, let's make this angle here be, let's make this angle, how about, why am I dumb? I'm going to make this 30 degrees, okay? So that means that this is 60 degrees. And so my perpendicular guy there is going to be, so, phooey. All right, so we'll make this force be 8 newtons again. So my perpendicular component all right. So another thing you can do is sometimes it's easier to find the component of the lever arm that is perpendicular to the force, okay? So suppose I had this. Suppose I had a wrench that was at a weird angle like this. And suppose I pulled on it with a force. Let's call this force number 4, and maybe it's 8 newtons, okay? All right? So, so one option would be to measure your lever arm. So this would be your lever arm, D. And then what you'd have to do is you'd have to find the component of the force that's perpendicular to that. So you'd go, all right, well, here's my force 4 perpendicular, here's my force 4 parallel, and then whatever this is, multiply it by D, and that would be your torque. But doing that would require knowing this angle and all kinds of stuff, right? So often what's easier is to do this. My force is vertical, right? So this displacement vector, or this lever arm, is a vector. So what we can do is just use the parallel, or sorry, the component of this lever arm that's perpendicular to my force. In other words, there's D perpendicular, okay? And my force is pulling perpendicular to that now, okay? So if I simply measure the length of from here to here, so the length of this little red line, that's my D perpendicular, because that's the component of the lever arm that's perpendicular to my given force. Okay, so let's see, let's actually measure this. So we'll use my stupid little ruler here, and it looks like it's about 6 centimeters. So here I can say, oh, well, torque is force times D perpendicular. So that's 8 newtons times 0.6 meters, which gives you what, 4.8 newton meters, right? And again, negative, because that's going to make it spin clockwise. Okay? All right, so that's that. Okay, now, so that's how you calculate torque. The torque is produced by force, depends on the length of your lever arm, and the component of the force, which is perpendicular to said lever arm. All right, now, I already alluded to this fact, but we have learned that the net force on an object, well, let me do it this way, actually. The linear acceleration of an object is equal to the net force divided by the mass. And remember, mass is inertia. Okay? So, Newton's second law for angular motion tells us that the angular acceleration is the net torque divided by I, the rotational inertia, okay, which we learned about in the last video, right? Okay? So, in the last video, we talked a whole bunch about how to calculate this rotational inertia, so I'm not going to go through that again. So, to calculate the angular acceleration, you find your net torque produced by the forces, divide it by the rotational inertia, and that gives you your alpha. Okay? And we did a bunch of these last year, okay? So, that's that. Oh, here, notice you got to measure your alpha in radians per second squared, okay? Oh, and here's a little bit of where that net torque equation comes from, if you want to follow through the algebra there. Most of you don't really care, probably. Okay, so let's do an example, all right? So here's the deal. This is what's new for this. All right, so here we've got these two blocks. So we got block 1 over here, which is 2 kilograms. We got block 2 over here, which is 6 kilograms. And we've got this pulley, all right? Now, the pulley has mass. Every other time we've done a problem, we've ignored the mass of the pulley. So this time, our pulley has a mass of 10 kilograms and a radius of 0.25 meters. All right? And as a result, to make the pulley spin, we need torque, right? Okay. So the question here would be find the tension in the rope and calculate the acceleration of the system. Okay? So here's the deal. If the pulley is massless, when we've done problems like this before, you know, the amorphous blob problems, what we did was we said that the tension at this end is the same as the tension at this end, right? But that's not going to be true here, because the idea is if our tension was equal, the pulley wouldn't spin, right? In other words, you'd have, you know, some force pulling the pulley this way, some force pulling the pulley that way. Those two forces would, the torques produced by those forces would cancel out and the pulley wouldn't spin. All right? So there are actually 3 unknowns in this problem. All right? So here are our unknowns. So for the 2 kilogram block, forces acting on the 2 kilogram box are the force of tension. I'm going to call it tension number 1. That's the tension over here on this side of the pulley. Okay? All right? Over here for the 6 kilogram box, you're going to have your FG parallel, which is 29.4 newtons. And then you've got another tension force, which I will call force of tension 2. Okay, that's pulling over here, tension 2. All right, so we got tension 1 pulling this way, tension 2 pulling this way. Oops, I wanted that to be blue. Tension 2 pulling this way. All right? All right, and then finally, the pulley. So now we've got this pulley, and there are 2 forces, and thus 2 torques applied to it. There's the force of tension 1 providing a torque, and there's the force of tension 2 providing a torque at a radius of 0.25 meters. Okay? So, and our 3 unknowns are force of tension 2, force of tension 1, and the acceleration of the system. Okay? So, in order to solve this, we need 3 equations, right? Well, guess what? We've got 3 objects, and each of those objects gives us an equation. Okay, so here we go. I'm going to write an equation. So the first equation I'm going to write is for the 2 kilogram thing. All right? So I guess I've neglected to say a few things here. So first of all, the pulley we can treat as a solid disk. Okay, and therefore I for a solid disk is, I have it written down on my paper here, 1/2 mr squared. All right, and secondly, for simplicity, let's assume everything here is frictionless, okay? You could certainly solve one with friction, but it's just more numbers to keep track of, right? But, you know, I would have to give you the coefficients of friction, and it would just be more forces on your drawings, okay? It doesn't make it harder, it just makes it more tedious, okay? So, let's solve this mess and see where we go, all right? So, for block number 1, here's what we know. We know that net force equals net force. So that means the force of tension number 1 equals mass times acceleration. Okay, so there is one of my equations. All right, now let's go over here to block number 2. For block number 2, same idea. Net force equals net force. So my net force is going to be, well, let's see. Let's take a look at this thing. So we got 29.4 newtons pulling down the ramp, right? 29.4 newtons pulling down the ramp, but there's nothing resisting the motion of the 2 kilogram block. So I'm guessing, not even guessing, I know my system's going to move this way, right? So let's call this way positive and this way negative. Okay? So my net force here is going to be 29.4 minus the force of tension 2. That's got to equal 6A, right? Okay, so that is another equation. So far I've got 2 equations but 3 unknowns, right? My red equation has FT1 and A, My blue equation has FT2 and A. So now the last thing I'm going to do is I'm going to write an equation for the pulley. And this is the piece that's new. All right? For the pulley, we're going to write an equation that says net torque equals net torque. Okay? So let me do this. Let's pull all of this down here. Give ourselves a little bit more room to work. Okay, so let's see. So for the pulley, net torque equals net torque. All right, so net torque. So this is I alpha equals the torque from tension 1 plus the torque from tension 2. Okay, so let's see. So I'm going to go over to the side and figure out what I is. I is 1/2 mr squared. So that's 1/2. The mass of this thing is 10 kilograms. It's a very heavy pulley. And our radius is 0.25 meters. Don't forget to square it. So multiply it all out, and you get 0.3125 kilogram meters squared. Okay? All right, so here we go. So I is 0.3125 times alpha. Alpha is not one of the variables I'm supposed to use, right? So alpha is, A over R. That's my connection, right? Okay, so when you deal with torque, you've got to use, remember, this is one of our jumper equations, right? On your equation sheet, it's A equals alpha R, right? So alpha is A over R. And we know R is 0.25. So alpha is A over 0.25, all right? So here's I. Alpha is A over 0.25 equals, I got to clear up some space here, so I'm going to erase. Okay, that equals the torque from tension 1 plus the torque from tension 2. So the torque from tension 1 is the force of tension 1 times 0.25, right? Force times radius. And notice, this is important. Notice your rope is always tangent to the circle and thus perpendicular to your radius. Okay, so this is perpendicular, this is perpendicular. Okay, and let's see, the torque from tension 1 is going to make this thing spin counterclockwise, right? So that one's going to be the positive one. This one's going to be the negative one, right? Is that right? Oh, shoot. I guess I got to be careful here. We want things spinning this way. And we have decided that was going to be a positive direction, right? So I need, no, I gotta make this way positive this time. Okay, because I need my angular acceleration. Remember when we did this up here, we said that this way was positive. So any torque contributing to motion that way, we need to call positive. Okay, because of this arbitrary system I set up here. Okay, so this one's going to be the positive one. This one's going to be the negative one. So this is negative plus the force of tension 2 times its lever arm, which is also 0.25 meters. Okay? So we can simplify that, and you get, so this is 0.2. Oh, wait, no, shoot. So this is force of tension 2 minus force of tension 1, all times 0.25 equals this mess. And if you divide both sides by 0.25, then you end up getting, how do I want to write this? It turns out to be 5A equals force of tension 2 minus force of tension 1. Okay? So now I have 3 equations and I need to solve them. Okay? So here are my 3 equations. This green guy and then the blue and the red from above. Okay? So let's go to a new page. So here we go. Red equation was force of tension 1 equals 2A. Blue equation was, oh shoot, how did I write it? I'm going to solve it for force of tension 2. So I'm going to add force of tension 2 and subtract 6A. give me this. Force of tension 2 equals 29.4 minus 6A. And then most recently, I came up with the green one, which was this. 5A equals force of tension 2 minus force of tension 1. All right, so 3 equations, 3 unknowns, solve it. So notice what I did is I solved 2 of my equations for 1 variable, right? So, or I expressed them in terms of 1 variable. So in other words, this is written in terms of A, this is written in terms of A. So now I'm going to plug them in down here. Okay? So what do we get? We get 5A equals force of tension 2 minus force of tension 1. So I'm looking at 5A equals 29.4 minus 8A. So add 8A, you get 13A equals 29.4. And so A is, I think it's 2.26 meters per second squared. So there's the acceleration of the system. Obviously, you can go back in and find your tension forces by plugging those in. So force of tension 1 ends up being 4.52 newtons. And force of tension 2 ends up being 15.83 newtons. All right. So what I want to point out here then is if you look at that wheel, let's take a look at that. Oops, let's look at the wheel. So here it is. We're drawing it in green. It's got a radius of 0.25. And so the force of tension 1 we just found, it's 4.52 newtons. I guess we should make it negative. Force of tension 2 was 15.83 newtons. So we can find our net torque and make sure that this works out. So first of all, notice that there's going to be more torque this way. So it's going to be 15.83 times 0.25. That's the torque from tension 2 minus 4.52 times 0.25. That's the torque from tension 1. So subtract those, and you get a number that I don't have written down, unfortunately. 15, oops. So it gives you 2.8275. So now we can check, right? Because alpha should be net torque over I. So 2.8275 is our torque. Our I was 0.3125, I think. Is that right? Let me double check my paper. Yep. So divide that out. And that gives us 9.048. And then A ought to be alpha R. So that's my alpha. This is radians per second squared. Radians per second squared. Let's multiply that by a radius of 0.25 meters. And it gives us 2.26 meters a second squared. Okay, so everything works out. All right? So, torque, there you go. That's about, well, close to as hard as they'll get. All right?